Welcome to another video of our PyTalk playlist. If you have stuck with us in our last video in where we have worked with text and tokenization. So today we are diving into some more advanced topics. In today's video, we are going to deal with LoRA or low-rank code and fine-tuning them using GPTs. Introduction to LoRA and fine-tuning with GPT, exploring use cases and mechanisms. Language models like OpenAI's GPT-3 and GPT-4 have transformed the landscape of artificial intelligence, offering unprecedented capabilities in text generation, translation, summarization, and more. However, deploying these powerful models for specific tasks can be challenging due to their size, computational requirements, and cost. This is where low-rank adaptation, LoRA, comes into play. LoRA allows for efficient fine-tuning of large language models, LLMs, with minimal resource requirements while maintaining high performance. This article explores LoRA, the fine-tuning process, and 3 use cases where LoRA-driven fine-tuning can significantly enhance outcomes. What is LoRA? LoRA stands for Low-Rank Adaptation of Large Language Models. It is a technique developed to efficiently fine-tune pre-trained large language models like GPT-3 and GPT-4 for specific tasks, while avoiding the need to modify the entire model's massive set of parameters. How does LoRA work? In large-scale language models, most parameters are often redundant for a specific downstream task. LoRA exploits this redundancy by assuming that the weight changes required for fine-tuning can be approximated with low-rank matrices. Instead of training all the model parameters, LoRA injects additional trainable parameters in the form of low-rank matrices, thereby preserving the majority of the model's pre-trained weights. To implement LoRA, low-rank decomposition, LoRA inserts low-rank decompositions into the attention weights of the language model. Mathematically, LoRA replaces a weight matrix W with the sum of 2 matrices plus W plus W, where W is factored into 2 smaller matrices of lower rank. These matrices have fewer parameters, reducing computational complexity. Trainable parameters. During fine-tuning, only these low-rank matrices are updated, while the original weights of the model remain unchanged. The task-specific knowledge is thus stored in these smaller, trainable matrices. Efficient computation. By keeping most of the model frozen and only adjusting the low-rank layers, LoRA reduces the number of trainable parameters by orders of magnitude, speeding up training times without significant loss in performance. So let's not waste time and get straight to work how things work behind the scene.
So let's get started. Stay along with me. Just a reminder, don't skip the steps and jump along the video if you're really willing to learn PyTorch in a proper way, as you may miss some climax and important steps. We are going to fine-tune LM using LoRA. As I have already noted, LoRA or low-rank adaptation LoRA is a machine learning technique that modifies a pre-trained model to better suit a specific, often smaller, dataset by adjusting only a small, low-rank subset of the model's parameters. So this will be your first GPT-trained video if you have stayed along the playlist. In previous video you have seen PyTorch and how to use it to work with text. In these videos we are leveling up with fine-tuning a text document using LoRA and predict the next word from it. Make sure to stay connected. You can even code along with me. You will find the repository link in the description. Do follow for more updates and coding content on latest tech. Enough talk, let's get to driver's seat. We will be having 2 files for this video, 1 module and 1 fine-tuning, that's the main file. And 1 GPT download file. The GPT download file may not work at the time you are watching, but anyway, we will get our work done without it. If you want script to download OpenAI GPT-2, join the Discord group for the files. Here we are already in the module file. I had already written the code, so stay along. I'll import OS from pathlib. Import path. Import urllib. Import zip file. Import matplotlib.pyplot as plt. Import numpy as np. Import pandas as pd. Import tick token. Import torch. Import torch.nn as nn. From torch.utils.data import dataset, data loader. Install all these packages using pip if your system lacked this package. Pip install packages. Class GPT to CV1 dataset. def__init_self txt tokenizer max_length stride. self.input_IDs. self.target_IDs. Tokenize the entire text. token underscore IDs tokenizer.encode txt allowed underscore special endolf text. Use a sliding window to chunk the book into overlapping sequences of max underscore length. For I in range 0, len token underscore IDs max underscore length, stride. Input underscore chunk token underscore IDs I max underscore length. Target underscore chunk token underscore IDs I1 I max underscore length 1. Self.input underscore IDs append torch.tensor input underscore chunk. Self.target underscore IDs append torch.tensor target underscore chunk. Def underscore len underscore self. Return len self.input underscore IDs. Def underscore getem underscore self IDX. Return self.input underscore IDs IDX, self.target underscore IDs IDX. Next, create a helper function. Def create underscore dataloader underscore v1 txt, batch underscore size 4, max underscore length 256. Stride 128, shuffle true, drop underscore last true. Initialize the tokenizer. Tokenizer ticktoken.get underscore encoding GPT2. Create dataset. Dataset GPT-cd1 txt, tokenizer, max underscore length, stride. Create dataloader. Dataloader. Dataset, batch underscore size, shuffle, drop underscore last. Return dataloader. Next, we are going to implement multi-head function. You must be wondering what's a multi-head function, as we will cover this topic in our upcoming playlist. For now, just to give you the glimpse of LLM and how fine-tuning ML model work, we are skipping that part. We will deal with coding mechanism and multi-headed properly in upcoming videos, so stay along. The playlist, everything will make sense. Class multi-head attention nn.module. Def underscore init underscore self, d underscore in, d underscore out, context underscore length, dropout, num underscore heads, qkv underscore bias false, super dot underscore init underscore. Assert d underscore out percent num underscore heads 0, d underscore out must be divisible by n underscore heads. Self dot d underscore out. Self dot num underscore heads num underscore heads. Self dot head underscore dim d underscore out num underscore heads, reduce the projection dim to match desired output dim. Self dot w underscore query nn dot linear d underscore in d underscore out bias qkv underscore bias. Self dot w underscore key nn dot linear d underscore in d underscore out bias qkv underscore bias. Self dot w underscore value nn dot linear d underscore in d underscore out bias qkv underscore bias. Self dot out underscore proj nn dot linear d underscore out linear layer to combine head outputs. Self dot dropout nn dot dropout. Self dot register underscore buffer mask torch dot tree torch dot one's context underscore length diagonal 1. Def forward self x b num underscore tokens d underscore in x dot shape. E self dot w underscore key x shape b num underscore tokens d underscore out. Queries self dot w underscore query x. Values self dot w underscore value x. We implicitly split the matrix by adding a num underscore heads dimension. Unroll last dim b num underscore tokens d underscore out b num underscore tokens num underscore heads head underscore dim. These keys dot view b num underscore tokens self dot num underscore heads self dot head underscore dim. Values dot view b num underscore tokens self dot num underscore heads self dot head underscore dim. Queries dot view b num underscore tokens self dot num underscore heads self dot head underscore dim. Transpose b num underscore tokens num underscore heads head underscore dim b num underscore heads num underscore tokens head underscore dim. These keys dot transpose 1 2. Queries dot transpose 1 2. values dot transpose 1 2. Compute scale dot product attention aka self-attention with a causal mask. ATN underscore scores queries at keys dot transpose 2 3 dot product for each head. Original mask truncated to the number of tokens and converted to Boolean. Mask underscore bool self dot mask dot bool colon num underscore tokens. Use the mask to fill attention scores. ATN underscore scores dot masked underscore fill underscore mask underscore bool dash torch dot nf. ATN underscore weights torch dot softmax ATN underscore scores keys dot shape dash 10.5 dim 1. ATN underscore weights self dot dropout ATN underscore weights. Shape B num underscore tokens num underscore heads head underscore dim. Context underscore VC ATN underscore weights at values dot transpose 1 2. Combine heads where self dot D underscore out self dot num underscore heads self dot head underscore dim. Context underscore VC dot reshape B num underscore tokens self dot D underscore out. Context underscore VC self dot out underscore proj context underscore VC optional projection. Return context underscore VC. Class layer norm NN dot module. Def underscore init underscore self EMB underscore dim. Super dot underscore init underscore. Self dot EPS 1E minus 5. Self dot scale NN dot parameter torch dot 1's EMB underscore dim. Self dot shift NN dot parameter torch dot 0's EMB underscore dim. Def forward self X. Mean X dot mean dim dash 1 keep dim true. Var X dot var dim dash 1 keep dim true unbiased false. Norm underscore XX mean torch dot sqrt var self dot EPS. Return self dot scale norm underscore X self dot shift. Class gilu NN dot module. Def underscore init underscore self. Super dot underscore init underscore. Def forward self X. Return 0.5x1 torch dot tan. Torch dot sqrt torch dot tensor 2 dot 0 torch dot pi. X 0.044715 torch dot pow x3. Class feed forward NN dot module. Def underscore init underscore self CFG. Super dot underscore init underscore. Self dot layers NN dot sequential. NN dot linear CFG EMB underscore dim 4 CFG EMB underscore dim. Jilu. NN dot linear 4 CFG EMB underscore dim CFG EMB underscore dim. Def forward self X. Return self dot layers X. Now we are getting to our badass boy. That's the transformer, not the typical Bumblebee or Optimus Prime or even Cybertron. It's encode and decoder. If you have stayed along the playlist, I have mentioned it in the previous chapter anyway, someone new to it. The transformer architecture is split into two distinct parts, the encoder and the decoder. These components work in conjunction with each other and they share a number of similarities. You can see the workflow diagram. Class transformer block nen.module. Def underscore init underscore self scag. Super dot underscore init underscore. Self dot at multiheadadantion. D underscore in scag emb underscore dim. D underscore out kev emb underscore dim. Context underscore length feg context underscore length. Num underscore heads feg n underscore heads. Dropout sef drop underscore rate. QQ underscore bias chef QG underscore bias. Self dot f feed forward feg. Self dot norm 1 layer norm seg emb underscore dim. Self dot norm 2 layer norm sfeg m underscore dim. Self dot drop underscore recede nn dot dropout feg drop underscore rate. Def forward self x. Shortcut connection for attention block. Shortcut x. X self dot norm 1x. xself.at xshape batch underscore size num underscore tokens m underscore size xself.drop underscore resid xx shortcut add the original input back. Shortcut connection for feed forward block. Shortcut x xself.norm2x xself.fx xself.drop underscore resid xx shortcut add the original input back. Return x. Class GPT model nen.model def underscore underscore init underscore underscore self fag super dot underscore underscore init underscore underscore self dot tuck underscore mnn dot embeddings vocab underscore size screm underscore dim self dot pose underscore mnn dot embedding squontext underscore length feg m underscore dim self dot drop underscore mnn dot dropout kek drop underscore rate self dot tref underscore blocks nn dot sequential transformer block fag for underscore in range fag n underscore layers self dot final underscore norm layer norm scag m underscore dim self dot out underscore head nn dot linear feg m underscore dim feg vocab underscore size bias false def forward self in underscore idx batch underscore size cq underscore len underscore idx dot shape talk underscore embed self dot talk underscore m in underscore idx pose underscore embed self dot pose underscore m torch dot orange cq underscore len device in underscore idx dot device xtalk underscore embeds pose underscore embed shape batch underscore size num underscore tokens im underscore size xself dot drop underscore mbx xself dot tref underscore blocks xself dot final underscore norm x logits self dot out underscore head x return logits. Next we are going for another helper function generate text simple model. Def generate underscore text underscore simple model idx max underscore new underscore tokens context underscore size idx is t array of indices in the current context for underscore in range max underscore new underscore tokens crop current context if it exceeds the supported context size, e.g. if LLM supports only 5 tokens and the context size is 10. Then only the last 5 tokens are used as context. idx underscore cond idx context underscore size. Get the predictions. With torch.no underscore grad. Logits model idx underscore cond. Focus only on the last time step. Batch n underscore token vocab underscore size becomes batch vocab underscore size. Logits -1. Get the idx of the vocab entry with the highest logits value. idx underscore next torch.argmax logits dim 1 keep dim true batch 1. Appends sampled index to the running sequence. idx torch.cat idx underscore next dim 1 batch n underscore tokens 1. Return idx. Def assign left, right. If left dot shape, right dot shape. Raise value where f shape mismatch. Left dot shape, right dot shape. Return torch.nn dot parameter torch.tensor right. Def load underscore weights underscore into underscore GPT params. GPT.pose underscore emb.weight assign GPT.pose underscore emb.weight params wb. GPT.talk underscore emb.weight assign GPT.talk underscore emb.weight params wt. For b in range len params blocks. U underscore w k underscore w v underscore wnp dot split. Params blocks BATT underscore ATN W3 axis 1. GPT.trf underscore blocks B.ATDTW underscore query dot weight assign. GPT.trf underscore blocks B.ATT.W underscore query dot weight Q underscore W dot T. GPT.trf underscore blocks B.ATTW underscore key dot weight assign. GPT.trf underscore blocks b.attd.w underscore key.weight k underscore w.t GPT.trf underscore blocks b.at.w underscore value.weight assign GPT.trf underscore blocks b.att underscore value.weight v underscore w.t q underscore b k underscore b v underscore bnp dot split params blocks batnc underscore atnb 3 axis 1 GPT.trf underscore blocks b.att.w underscore query dot bias assign GPT.trf underscore blocks b.at.w underscore query dot bias q underscore b GPT.trf underscore blocks b.att.w underscore key dot bias assign GPT.trf underscore blocks b.att.w underscore key dot bias k underscore b GPT.trf underscore blocks b.att.w underscore value dot bias assign GPT.trf underscore blocks b.att.w underscore value dot bias v underscore b GPT.trf underscore blocks b.at.out underscore proj dot weight assign GPT.trf underscore blocks b.att.out underscore proj dot weight params blocks batnc underscore proj w.t GPT.trf underscore blocks b.att.out underscore proj dot bias assign GPT.trf underscore blocks b.at.out underscore proj dot bias params blocks batnc underscore proj b GPT.trf underscore blocks b.ff.layers 0 dot weight assign GPT.trf underscore blocks b.ff.layers 0 dot weight params blocks bmlpc underscore fcw.t GPT.trf underscore blocks b.ff.layers 0 dot bias assign GPT.trf underscore blocks b.ff.layers 0 dot bias params blocks bmlpc underscore fcb GPT.trf underscore blocks b.ff.layers 2 dot weight assign GPT.trf underscore blocks b.ff.layers 2 dot weight params blocks bmlpc underscore proj w.t GPT.trf underscore blocks b.ff.layers 2 dot bias assign GPT.trf underscore blocks b.ff.layers 2 dot bias params blocks bmlpc underscore proj b GPT.trf underscore blocks b.norm1 dot scale assign GPT.trf underscore blocks b.norm1 dot scale params blocks bln underscore 1g GPT.trf underscore blocks b.norm1 dot shift assign GPT.trf underscore blocks b.norm1 dot shift params blocks bln underscore 1b GPT.trf underscore blocks b.norm2 dot scale assign GPT.trf underscore blocks b.norm2 dot scale params blocks bln underscore 2g GPT.trf underscore blocks b.norm2 dot shift assign GPT.trf underscore blocks b.norm2 dot shift params blocks bln underscore 2b GPT.final underscore norm dot scale assign GPT.final underscore norm dot scale params g GPT.final underscore norm dot shift assign GPT.final underscore norm dot shift params b GPT.out underscore head dot weight assign GPT.out underscore head dot weight params wte def text underscore to underscore token underscore IDs text tokenizer the encoded tokenizer dot encode text allowed underscore special asa in dov text apane encoded underscore tensor torch dot tensor encoded dot unsqueeze 0 add batch dimension return encoded underscore tensor def token underscore IDs underscore to underscore text token underscore IDs tokenizer flat token underscore IDs dot squeeze 0 remove batch dimension. Return tokenizer dot decode flat dot tallest. Def calc underscore loss underscore loader data underscore loader model device num underscore batches none. Total underscore loss 0. If len data underscore loader 0. Return float nan. Elif num underscore batches is none. Num underscore batches len data underscore loader. Else. Reduce the number of batches to match the total number of batches in the data loader. If num underscore batches exceeds the number of batches in the data loader. Num underscore batches min num underscore batches len data underscore loader. For I input underscore batch, target underscore batch and enumerate data underscore loader. If I num underscore batches, loss calc underscore loss underscore batch input underscore batch, target underscore batch model device. Total underscore loss loss dot item. Else. Break. Return total underscore loss num underscore batches. Def evaluate underscore model train underscore loader val underscore loader device eval underscore iter model dot eval with torch dot no underscore grad train underscore loss calc underscore loss underscore loader train underscore loader model device num underscore batches eval underscore iter val underscore loss calc underscore loss underscore loader val underscore loader model device num underscore batches eval underscore iter model dot train. Return train underscore loss val underscore loss. Def download underscore and underscore unzip underscore spam underscore data URL zip underscore path extracted underscore path data underscore file underscore path. If data underscore file underscore path dot exists. Print f data underscore file underscore path already exists. Skipping download and extraction. Return. Downloading the file. With urlib.request.urlopen URL as response. With open zip underscore path, WB as out underscore file. Out underscore file dot write response dot read. Unzipping the file. With zipfile.zipfile zip underscore path, R as zip underscore ref. Zip underscore ref dot extractl extracted underscore path add dot tsv file extension original underscore file underscore path extracted underscore path sms spam collection os dot rename original underscore file underscore path data underscore file underscore path print f file downloaded and saved as data underscore file underscore path def create underscore balanced underscore dataset df count the instances of spam. Num underscore spam df label spam dot shape 0. Randomly sample ham instances to match the number of spam instances. Ham underscore subset df label ham dot sample num underscore spam random underscore state 123. Combine ham subset with spam. Balanced underscore dfpd dot concat ham underscore subset df label spam return balanced underscore df. Def random underscore split df, train underscore frac, validation underscore frac, shuffle the entire data frame. df dot sample frac 1, random underscore state 123 dot reset underscore index drop true. Calculate split indices. Train underscore end int len df train underscore frac. Validation underscore end train underscore end int len df validation underscore frac. Split the data frame. Train underscore df train underscore end. Validation underscore df train underscore end validation underscore end. Test underscore df validation underscore end. Return train underscore df validation underscore df test underscore df. Class spam dataset df underscore init underscore self csv underscore file tokenizer max underscore length none pad underscore token underscore id 5256 self.data.pd.read_csv_csv_file. Pre-tokenized texts. Self.encoded_texts. Tokenizer.encode text for text in self.data text. If max_length is none. Self.max_length self._longest_encoded_length. False. Self.max_length max_length. Truncate sequences if they are longer than max_length. Self.encoded_texts. Encoded_text self.max_length. For encoded_text in self.encoded_texts. Add sequences to the longest sequence. Self.encoded_texts. Encoded_textpad_token_id self.max_length len encoded_text. For encoded_text in self.encoded_text. Def__getting_self, index. Encoded self.encoded_texts, index. Label self.data.iloc index label. Return torch.tensor encoded, detype torch.long torch.tensor label, detype torch.long. Def__len_self. Return len self.data. Def_longest_encoded_length self. Max_length 0. Encoded_text in self.encoded_texts. Encoded_length len encoded_text. If encoded_length max_length. Max_length encoded_length. Return max_length. At torch.no_grad disable gradient tracking for efficiency. Def calc_accuracy_loader data_loader model device num_batches none. Model.eval. Correct_predictions num_examples 0, 0. If num_batches is none. Num_batches len data_loader. Else, dengd. Num_batches min num_batches len data_loader. For I input_batch, target_batch in enumerate data_loader. If I num_batches. Input_batch, target_batch input_batch dot to device, target_batch dot to device. Logits model input_batch, -1, logits of last output token. Predicted_labels torch.argmax logits, dim1. Num_examples predicted_labels shape 0. Correct_predictions predicted_labels target_batch.sum.item. And else. Break. Return correct_predictions num_examples. Def calc_loss_batch input_batch target_batch model device. Input_batch target_batch input_batch dot to device target_batch dot to device. Logits model input_batch -1 logits of last output token. Loss torch.nn.functional.cross_entropy logits target_batch. Return loss. Overall the same as train_model_simple in chapter 5. Def train_classifier_simple model, train_loader, val_loader, optimizer device, num_epochs. Eval_frake, eval_iter. Initialize lists to track losses and tokens seen. Train_losses, val_losses, train_ACs, val_ACCs, examples_seen, global_step 0, -1. Main training loop. Epoch in range num_epochs. Model.train set model to training mode. For input_batch, target_batch and train_loader. Optimizer.0_grad reset loss gradients from previous batch iteration. Loss calc_loss_batch input_batch target_batch model device. Loss.backward calculate loss gradients. Optimizer.step update model weights using loss gradients. Examples underscore scene input underscore batch dot shape 0 new track examples instead of tokens. Global underscore step 1. Optional evaluation step. If global underscore step percent eval underscore frec euro. Train underscore loss, val underscore loss evaluate underscore model. Model, train underscore loader, val underscore loader, device, eval underscore iter. Train underscore losses dot append train underscore loss. Val underscore losses dot append val underscore loss. Print FEP epoch 1 step global underscore step 06D. F train loss colon dot 3F, val underscore loss colon dot 3F. Calculate accuracy after each epoch. Train underscore accuracy calc underscore accuracy underscore loader train underscore loader model device num underscore batches eval underscore iter. Val underscore accuracy calc underscore accuracy underscore loader val underscore loader model device num underscore batches eval underscore iter. Print F training accuracy train underscore accuracy 100 colon dot 2F% end. Print F validation accuracy val underscore accuracy 100 colon dot 2F%. Train underscore ACZs dot append train underscore accuracy. Val underscore ACZs dot append val underscore accuracy. Return train underscore losses, val underscore losses, train underscore ACZs, val underscore ACC examples underscore scene. Def plot underscore values epochs underscore scene, examples underscore scene, train underscore values, val underscore values, label loss. Fig, ax1 plt dot subplots fig size 5.3. Plot training and validation loss against epochs. ax1 dot plot epochs underscore scene, train underscore values, label F training label. ax1 dot plot epochs underscore scene, val underscore values, line style label F validation label. ax1 dot set underscore x label epochs. ax1 dot set underscore y label dot capitalize. ax1 dot legend. Create a second x-axis for tokens scene. ax2 ax1 dot 20 create a second x-axis that shares the same y-axis. ax2 dot plot examples underscore scene, train underscore values, alpha 0 invisible plot for aligning ticks. ax2 dot set underscore x label examples scene. Fig dot tight underscore layout adjust layout to make room. plt dot save fig f label dash plot dot pdf. plt dot show.
So we have completed our first part and the module. Give yourself a thumbs up if you have stuck so far and completed the steps. Let's get into our main file, that's the fine-tuning with LoRA. So if you are tired, feel free to grab some water as the main part is on its way. Let's get started.
Now we are getting into our file fine-tuning with LoRA. Let's get started. Import all the packages. If your system lacked the package, make sure to install it by using pip install packages. Follow along to get things making sense. From importlib.metadata import version, pkg's matplotlib, numpy, tick token, torch, pandas for p in pkgs. Print fp version p. This will show you the version of the packages. Next we are going to prepare the dataset. From pathlib import path. Import pandas as pd. From previous underscore chapters import. Download underscore and underscore unzip underscore spam underscore data. Create underscore balanced underscore dataset. Random underscore split. URL https://github.com/suruj-kalita/pytorch-forward/main/sms%5b-spam%5d.zip. Zip underscore path sms underscore spam underscore collection.zip. Extracted underscore path sms underscore spam underscore collection. Data underscore file underscore path extracted underscore path sms spam collection.tsv. download underscore and underscore unzip underscore spam underscore data URL, zip underscore path, extracted underscore path, data underscore file underscore path, dfpd.read underscore csv data underscore file underscore path, sept, header none, names label, text. Balanced underscore df create underscore balanced underscore dataset df. Balanced underscore df label balanced underscore df label dot map ham 0 spam 1. Train underscore df validation underscore df test underscore df random underscore split balanced underscore df 0.7 0.1. Train underscore df dot to underscore csv train dot csv index none. Validation underscore df dot to underscore csv validation dot csv index none. Test underscore df dot to underscore csv test dot csv index none, but you will find the directory link in the description. Even if you are following along, you are going to the same things in result. This will download the spam SMS file in your project directory. Import torch. From torch.utils.data import dataset. Import tick token. From previous underscore chapters import spam dataset. Tokenizer tick token dot get underscore encoding GPT-2. Train underscore dataset spam dataset train dot csv max underscore length none tokenizer. Val underscore dataset spam dataset validation dot csv max underscore length train underscore dataset dot max underscore length tokenizer. Test underscore dataset spam dataset test dot csv max underscore length train underscore dataset dot max underscore length tokenizer. Next we going importing the data loader. From torch.utils.data import data loader. Num underscore workers 0. Batch underscore size 8. Torch.manual underscore seed 123. Train underscore loader data loader. Dataset train underscore dataset. Batch underscore size batch underscore size. Shuffle true. Pace. Num underscore workers num underscore workers. Drop underscore last true. Val underscore loader data loader. Dataset val underscore dataset. Batch underscore size batch underscore size. Num underscore workers num underscore workers. Drop underscore last false. Test underscore loader data loader. Dataset test underscore dataset. Batch underscore size batch underscore size. Num underscore workers num underscore workers. Drop underscore last false. As a verification step, we iterate through the data loaders and check that the batches contain 8 training examples each, where each training example consists of 120 tokens. Print train loader. For input underscore batch, target underscore batch and train underscore loader. Pass. Print input batch dimensions, input underscore batch dot shape. Print label batch dimensions, target underscore batch dot shape. Lastly, let's print the total number of batches in each dataset. Print flen train underscore loader training batches. Print flen val underscore loader validation batches. Print flen test underscore loader test batches. Now we getting into our bad boy that's initializing the model. This kernel is the heart of our file, so make sure you don't skip any stages. From GPT underscore download import download underscore and underscore load underscore GPT-2. From module import GPT model, load underscore weights underscore into underscore GPT. Choose underscore model GPT-2, small 124M. Input underscore prompt every effort moves. Base underscore config. Vocab underscore size 50257, vocabulary size. Context underscore length 1024, context length. Drop underscore rate 0.0, dropout rate. QKV underscore bias true query key value bias. Model underscore configs. GP2 small 124M EMB underscore dim 768, N underscore layers 12, N underscore heads 12. GP2 medium 355 MEMB underscore dim 1024 N underscore layers 24 N underscore heads 16. GPT2 large 774 MEMB underscore dim 1280 N underscore layers 36 N underscore heads 20. GP2 XL 1558 MEMB underscore dim 1600 N underscore layers 48 N underscore heads 25. Base underscore config dot update model underscore configs choose underscore model. Model underscore size choose underscore model dot split dash 1 dot ulstrip dot rstrip. Settings params download underscore and underscore load underscore GPT2 model underscore size models underscore D or GPT2. Model GPP model base underscore config. Load underscore weights underscore into underscore GPT model params. Model.eval. This will take some time. Keep patience. Grab some water as stay along. After completing the download, you will find the file in the folder of your repository. Be careful of one word, that's the input prompt. If the input prompt is not present on our sms.spam file, it will not generate the next coherent text, so make sure you have that line of text in the file. If yes, you are good to go. To ensure that the model was loaded corrected, let's double check that it generates coherent text. From module import. Generate underscore text underscore simple. Text underscore to underscore token underscore IDs. Token underscore IDs underscore to underscore text. Text underscore 1 every effort moves you. Token underscore IDs generate underscore text underscore simple. Model. IDX text underscore to underscore token underscore IDs text underscore 1 tokenizer. Max underscore new underscore tokens 15. Context underscore size base underscore config context underscore length. Print token underscore IDs underscore to underscore text token underscore IDs tokenizer. Then we prepare the model for classification fine-tuning, where we replace the output layer. Torch.manual underscore seed 123. Num underscore classes 2. Model.out underscore head torch.nn.linear in underscore features 768. Out underscore features num underscore classes. Device torch.device CUDA if torch.CUDA is underscore available else CPU. Note: uncommenting the following lines will allow the code to run on Apple Silicon chips, if applicable, which is approximately 1.2x faster than on an Apple CPU, as measured on an M3 MacBook Air. However, the resulting loss values may be slightly different. If torch.CUDA is underscore available, device torch.device CUDA. Elif torch.backends.mps is underscore available, device torch.device MPs. Else, one more relay. Device torch.device CPU. Print F using device. Model.to-device, no assignment model.to-device necessary for NN.module classes. Lastly, let's calculate the initial classification accuracy of the non-fine-tuned model. We expect this to be around 50%, which means that the model is not able to distinguish between spam and non-spam messages yet reliably. From module import calc underscore accuracy underscore loader. Torch.manual underscore seed 123. Train underscore accuracy calc underscore accuracy underscore loader train underscore loader model device num underscore batches 10. Val underscore accuracy calc underscore accuracy underscore loader val underscore loader model device num underscore batches 10. Test underscore accuracy calc underscore accuracy underscore loader test underscore loader model device num underscore batches 10. Printf training accuracy train underscore accuracy 100:2f%. Printf validation accuracy val underscore accuracy 100:2f%. Printf test accuracy test underscore accuracy 100:2f%. Next we are going to parameter efficient fine-tuning with LoRA. Import math. Class LoRA layer torch.nn.module. Def underscore underscore init underscore underscore self in underscore dim out underscore dim rank alpha. Super dot underscore underscore under underscore underscore underscore. Self dot a torch dot nn dot parameter torch dot empty in underscore dim rank. Torch dot nn dot init dot ending underscore uniform underscore self dot a math dot sqrt5 similar to standard weight initialization. Self.b torch.nn parameter torch.zeros rank out underscore dim. Self.alpha alpha alpha. Def forward self x. X self.alpha x at self.a at self.b. Return x. To incorporate the original linear layer weights as shown in the figure above, we implement a linear with LoRA layer below that uses the previously implemented LoRA layer and can be used to replace existing linear layers in a neural network, for example. The self-attention module or feed-forward modules in an LLM. Class linear with LoRA torch.nn.module. Def underscore underscore init underscore underscore self linear rank alpha. Super dot underscore underscore init underscore underscore. Self dot linear linear. Self dot LoRA LoRA layer. Linear dot in underscore features, linear dot out underscore features, rank alpha. Def forward self, x. Return self dot linear x self dot LoRA x. To try LoRA on the GPT model we defined earlier, we define a replace underscore linear underscore with underscore LoRA function to replace all linear layers in the model with the new linear with LoRA layers. Below is the workflow diagram how things are going under the hood. This shows how text are tokenized and generated by the LLM model. Def replace underscore linear underscore with underscore LoRA model rank alpha. For name, module in model.named underscore children. If instance module, torch.nn.linear. Replace the linear layer with linear with LoRA. Setator model, name, linear with LoRA module, rank alpha. Else. Menkoi. Recursively apply the same function to child modules. Replace underscore linear underscore with underscore LoRA module, rank alpha. We then freeze the original model parameter and use the replace underscore linear underscore with underscore LoRA to replace the said linear layers using the code below. This will replace the linear layers in the LLM with linear with LoRA layers. Total underscore params sum p dot numal for p in model dot parameters if p dot requires underscore grad. Print f total trainable parameters before total underscore params. For param in model dot parameters. Param dot requires underscore grad false. Total underscore params sum p dot numal for p in model dot parameters if p dot requires underscore grad. Print f total trainable parameters after total underscore params. Replace underscore linear underscore with underscore LoRA model, rank 16, alpha 16. Total underscore params sum p dot numal for p in model dot parameters if p dot requires underscore grad. Print f total trainable LoRA parameters total underscore params. As we can see, we reduced the number of trainable parameters by almost 50x when using LoRA. Let's now double-check whether the layers have been modified as intended by printing the model architecture. Device torch.device CUDA if torch.CUDA is underscore available else CPU. Model dot to device. Print model. Based on the model architecture above, we can see that the model now contains our new linear with LoRA layers. Also, since we initialized matrix $B with zeros, we expect the initial model performance to be unchanged compared to before. Torch.manual underscore seed 123. Train underscore accuracy calc underscore accuracy underscore loader train underscore loader model device num underscore batches 10. Val underscore accuracy calc underscore accuracy underscore loader val underscore loader model device num underscore batches 10. Test underscore accuracy calc underscore accuracy underscore loader test underscore loader model device num underscore batches 10. Print f training accuracy train underscore accuracy 100:2f%. Print f validation accuracy val underscore accuracy 100:2f%. Print f test accuracy test underscore accuracy 100:2f%. Let's now get to the interesting part and fine-tune the model. The training takes about 15 minutes on a M3 MacBook Air laptop computer and less than half a minute on a V100 or a 100 GPU. Import time. From module import train underscore classifier underscore simple. Start underscore time dot time. Torch.manual underscore seed 123. Optimizer torch.optim.atomomodel.parameters LR5E5 weight underscore decay 0.1. Num underscore epochs 5. Train underscore losses, val underscore losses, train underscore ACs, val underscore ACCs, examples underscore scene train underscore classifier underscore simple. The model, train underscore loader, val underscore loader, optimizer, device. Num underscore apox num underscore epochs, eval underscore freq50, eval underscore iter 5. End underscore time dot time. Execution underscore time underscore minutes end underscore time start underscore time 60. Print f training completed in execution underscore time underscore minutes dot 2f minutes. After the training completed, jump to the take step. Finally, let's evaluate the model. From previous underscore chapters, import plot underscore values. Epochs underscore tensor torch dot linspace 0, num underscore epochs, len train underscore losses. Examples underscore scene underscore tensor torch dot linspace 0, examples underscore scene, len train underscore losses. Plot underscore values epochs underscore tensor, examples underscore scene underscore tensor, train underscore losses, val underscore losses, label loss. Feel free, as you are going to get all the plotting and score in a PDF format in the folder. Make sure to give it a look. Next, we have almost reached the end of our video. We are going to calculate training accuracy. This may take some minute. I have already run the kernel. Make sure you do the same. Train underscore accuracy calc underscore accuracy underscore loader train underscore loader model device. Val underscore accuracy calc underscore accuracy underscore loader val underscore loader model device. Test underscore accuracy calc underscore accuracy underscore loader test underscore loader model device. Print f training accuracy train underscore accuracy 100:2f%. Print f validation accuracy val underscore accuracy 100:2f%. Print f test accuracy test underscore accuracy 100:2f%. So you have successfully found your first large language model using LoRA. Gives a thumbs up to yourself. If you have stayed so far, make sure to stay tuned and like the video and stay connected for upcoming videos.
So summarizing things, as we have completed fine-tuning with LoRA, hope you have got some of the glimpse how PyTorch and large language models work. You will unlock more topics in our upcoming videos in our PyTorch playlist. In this exploration of LoRA, low-rank adaptation, and fine-tuning large language models like GPT, we've seen how this innovative approach dramatically enhances the efficiency and scalability of AI-powered solutions. By focusing on a small set of trainable parameters, LoRA allows organizations to fine-tune massive models like GPT-3 and GPT-4 for specific tasks without requiring vast computational resources or time. From healthcare chatbots providing specialized medical advice to financial document summarization, LoRA opens the door to fine-tuning AI models for real-world applications, efficiently tailoring them for industry-specific needs. This breakthrough is a game-changer, especially for organizations looking to leverage advanced AI without the burden of costly infrastructure. As AI continues to push boundaries, techniques like LoRA ensure that powerful models remain adaptable, efficient, and accessible, enabling the next generation of AI-driven innovations. So see you next time. Till then, goodbye. Make sure to subscribe and like for latest upcoming videos.